In this video, you will be learning the design and detailing of reinforced concrete column that is a part of intermediate moment resisting frame. The framing plan is shown. C1 are exterior columns and C2 is interior columns. We have to design these columns. The FC prime is 4 kSi and FI is 60 kSi. It's a two-story structure. The center to center span is 8 feet and the slab is 8 inches. Live load is 40 psf. Super dead load is 20. The seismic zone is 2B. The soil type is SD and it is a moment resisting frame. Residential building type, we have to use UBC 97 for seismic loading. Calculate the column sizes, design reinforcement and detail the column drawing using ACI 31814. First of all, we have to calculate the rough dimensions of the column. The maximum column catchment area is 18 feet by 18 feet. Calculating the ultimate load for slab self and 20 psf super dead, 1.6 times 40 gives us ultimate load of 208 psf. Multiplying the ultimate load by the catchment area gives us load in pounds. For the cross-sectional area, we divide with the strength of the column material, that is FC prime, and reducing it to 40%. Typically, we don't take column less than 8 inches, so we will define sizes near to 8 inches or higher. The seismic zone 2B, and so the frame is to be taken as intermediate moment resisting frame. First of all, we will be defining the grids. The grids are now defined for the two-story structure. After defining the grids, the first step will be defining the material properties. 4 psi concrete is already defined. Let's check the modulus of elasticity for 4 psi. 4000 under root multiplied by 57000 and the value is same. Adding the material for rebar. Let's call it G60 deformed. Now we will be defining the frame sections. Let's delete the useless sections. Starting with 10 inch by 10 inch column. Applying the property modifiers using ACI code for column is 0.7 times gross moment of inertia to incorporate the cracking. Reinforcement to be designed is to be selected. Since we have selected reinforcement to be designed, then The only thing important here is the column cover, while the rest of the things such as the bars and this area is not important to be defined since we have selected reinforcement to be designed. If we selected reinforcement to be checked, then this lower portion in the column modification is important. So we will check the reinforcement to be designed option. Add the copy of property with different dimensions. Let's call C12 by C12. The properties, rest of them are same. C14 by C14. If we want Etabs to select itself the properties of the column size, we will define another section as well later on. Defining the slab properties as 8 inches and taking the slab as shell thin. In order to understand the difference between shell thin and membrane, go to the previous videos. Taking slab modifiers as 0.25 of the gross moment of inertia using ACI code to incorporate the cracking in the slab. The cracks are flexures, so we incorporate in the bending. Delete the rest of the useless properties. Now defining the load pattern. Super dead load. Earthquake in X direction. And earthquake in Y direction. Defining the parameters for the earthquake loading. The soil type is SD and the zone is 2B. So for zone 2B, we need to go to UBC 97 chapter 16. The zone factor is 0.2. Since we have selected the zone factor 0.2, Etabs 2016 will automatically select values of CA and CV. You may check the values of CA and CV from the code chapter 16. The values were okay. The CT value for concrete is 0.03 in order to calculate the time period of the structure. It is important to take the base of the structure as the level which is above the ground or the natural ground. For concrete IMRF, the strength reduction factor is 0.5 since the earthquake structures or structures for seismic are designed for damage. The importance factor for standard occupancy is 1 since it's a residential structure. Defining the same parameters in Y direction. Now adding the mass source. The dead load multiplier 1 times the live load. Live load shall be added in the structure having a height greater than 100 feet usually and 25% of that will be incorporated. Since our structure is having height lower than 100 feet, so we won't add the live load case in the mass source. Now we will be defining the auto select option so that we give Etabs a choice that it will automatically select the size of the column from the defined sections of the column. Auto select and concrete. So we have to select these columns and import in auto select list. Starting section auto select list, you have to start from the minimum area. You can also specify a specific column property so that Etabs start the iterations from that particular column. We will be drawing the column using the auto select option. Since it's a flat plate system, now we will have to match and assign the loads to the slab. First, selecting the slabs. The slab is 18 feet and the mesh size should not be greater than 3 feet. So we will get 6 areas in X direction and 6 areas in Y direction. So the slab is meshed now. Now next step is selecting the slab again and assigning the loads to the slab. We go to shell loads and then uniform loads. Assigning the live load as 40 PSF. Select again and then 20 PSF in SDL load case and then OK. Now set to default visibility options or just click on columns and beams. Now select all the columns, go to design, concrete frame design and view revise overrides. Since it is selected by default as SOI special, click on SOI intermediate. Since it is an intermediate moment resisting frame, let the section be whatever it is selected by Etabs as default. Now we will add the default design combinations for the concrete frame. You may check convert to user defined if you wish that you may further revise the combination. The combinations are added as default. Now the next step is to select those combinations which you will be using in the design. First of all, selecting the design code from the preferences and the design for the soil type. The design combinations are already added. Okay. Since we have added the design combinations in Etabs as well as the load gases. Now we are required to assign the diaphragm to the structure. Diaphragm basically distributes the lateral forces that come on the slab to the lateral force resisting members that are columns and shear walls. In our case here it is column. Since it is a symmetric structure, hence the forces will be translated in terms of x and y uniformly. Now P delta options are important to define. P delta options will carry out a second order analysis where additional moments are generated due to the deflected shape of the structure. Usually we select the same scale factor which we are using in combination. We won't add live load until the structure is of 100 feet height or above, and only 25% of live load contribution is added in the P delta facts. Now we need to replicate. In replication options, we need to select the diaphragms as well so that it replicates the diaphragm. To story 1 and then apply. Then our structure is replicated and the modeling is complete in terms of drawing the structural elements and assigning the loads and their properties. Now assigning fixed support to the column bottom, which will later on translate it to footings when we will be designing the footings in the next videos that will later come on. Now we need to run the model, closing all the additional windows that will not be useful. First we need to save the analysis model. And then we will be required to design the structure. For frame design, analysis and design differs for different concrete sections we wish to iterate. Yes, since we wish to keep the uniform design for exterior columns and interior columns distinct from exterior columns. Now it will run and redesign. Now we want only columns to be visible in this screen, so we will turn off the additional stuff. Usually when designing the earthquake frames, we have to check the things. The length of the column should be equal to the story length usually. Let's say our story height was 10 feet, then the 120 inches is adequate. And there is important another thing to be checked, the effective length factor, that is K factor. First of all, we need to know the column is short or slender. For braced frame, the criteria is shown, and for unbraced frame like our case that was a sway frame, the criteria is also shown. If the column is slender, then a moment magnifier method is used, but since we are using software, so it will automatically magnify the moment if required. So it's not important to know whether the column is short or slender, but for effective length we need to know. Usually we take a value of 1.0 conservatively if the column is supported at top and bottom. Usually the column is failed by Etabs, and if we don't check the effective length factor, then it will be not suitable for the design. So we are getting summary. We go to summary and check effective length factor of the columns randomly. Sway and non-sway factor, since the column is not slender, so the sway and non-sway multiplier factor is calculated as 1 by Etabs itself. So now we need to check which cross sections or the which column properties Etabs selected by itself. Let's convert it into rebar percentage. Firstly, we will be designing the exterior columns. Let's have a quick look on the cross-sectional area which Etabs has selected by itself. So the top steel is coming out to be higher than the bottom story steel. Usually it happens when we apply seismic loading. So the reason is, the further the column is from the support, that is base, the higher will be the moments in that part due to lateral force, and the higher will be steel. But logically we won't place the steel as shown. We will place the higher steel in any story in bottom first. That is also good to know from stability point of view. Since the higher percentage of the column is coming in the higher stories or the top story, we need to check thoroughly in all of the columns to get an idea what we will be incorporating in the design. So you see all the or most of the columns are getting higher steel. So Etabs has selected 10 by 10 for this cross section. Let's see what sizes Etabs has selected for the rest of the columns using auto select list option. Selected 12 by 12, 12 by 12, also 12 by 12, also 12 by 12, here also 12 by 12 and 12 by 12. Similarly 12 by 12 and 10 by 10 here. So now we will be unlocking the model and assigning all the column as 12 by 12. since there are very few columns with 10 by 10 dimensions. So to keep all exterior columns uniform in terms of dimension, we will assign them 12 by 12 cross section. But first we have to unlock the model. Let's redesign by overwriting. So now the percentage of steel are reduced, where Etabs was taking 10 by 10 as default section. Since the properties are overwritten and the forces may not be transferred according to the 12 by 12 cross section as we didn't reanalyze. So usually we need to rerun the model. Now I have hidden the columns of the top story. We will be looking at the percentage of steel in the lower story columns. The percentages of steel are less than the upper story columns. So for design point of view, we will be putting the higher steel, whether it's coming from the above story or the lower story, inside the column cross section of the bottom story. We need the area of steel in terms of percentage usually. So in each and every column, the higher value will be governing for all of the columns. So this is the framing plan and the structural drawing of the columns and the column layout. So first we will be starting with the column C1, that is the exterior columns from in the bottom story, plinth level to ground floor. The percentages of steel seams that they are higher in the top story and lower in the bottom story. But I will repeat this thing again, that we have to put the higher percentage of steel in the bottom section of the column, even if Etabs is giving lower percentage of steel in the bottom section. So now we will have to calculate the number of bars. The percentage of steel is 3.753 multiplied by 12 inch multiplied by 12 inch divided by 100, since the percentage was in percentage terms. So we are getting 5.4 inch square of steel for the bottom section of the column. So I would have reanalyzed the structure, assigning the 12 by 12 inch cross section so that forces are distributed according to their inertias and stiffness properties in spite of overwriting their properties. Now we will be again checking the steel for the columns C1 that are exterior columns. There is no need to worry that we are getting the steel higher in the above stories. So I once again use the auto select option to run the iteration once again. The Etabs is mostly selecting 12 by 12 cross section. So I select all of the columns at once and assign a uniform cross section, that is 12 by 12. Since the highest cross section taken by Etabs for exterior columns was 12 by 12. And then we will be designing the columns according to the new assigned cross section as suggested by Etabs from the previous design groups. So now we will display the reinforcement percentage in terms of rebar percentage of the gross area. So we are again getting the higher percentage in the top portion of the column and lower percentage in the bottom portion of the column. Definitely earthquake combination will be governing as the moment due to lateral force is higher in the top portion and lower in the lower portion. So we will use the higher percentage of steel in the bottom portion, that is 2.9% multiplied by 12 into 12 divided by 100 since it was in percentage terms. So it is 4.176 percentage inch square of steel required in the bottom portion. For number 6 bars, 4.176 divided by the area of the bar gives us 10 number 6. But since we have to keep the uniform number of bars on each space, so we intend to take 12 number 6 bars. The dimensions are 12 by 12 for the bottom story columns and exterior columns. That is 12 number 6 bars. Now we have to do the similar thing with the exterior column of the above story. Let's turn off the visibility of the ground floor story columns. Similarly, we are getting the same percentage of steel which we intentionally put in the lower story columns, which was higher definitely. So the steel will be same in the upper story as well. That is 12 number 6 bars. Rename adding the dimension as 12 inches for the column. So now we will be working on the interior columns. Show all objects. A turn off the visibility of the exterior columns whose longitudinal reinforcement is already designed. Hide selected objects. Interior columns are shown. named as C2. So the cross-sectional shape selected by Etabs for interior columns is 10 by 10 mostly, but we will select the higher area of concrete selected by Etabs since we intend to keep the cross-sections uniform for interior columns. So we will select all the columns and assign the higher cross-sectional area selected by Etabs for the typical set of the columns and rerun the analysis and then design. So we are getting a lower percentage of steel than the exterior column since it's a sway moment resisting frame. If it was designed only on gravity loads, then logically we will be getting the higher percentage of steel in the interior column since the column catchment area is higher. So the percentage of steel is 3.62 into 12 divided by 100 as it was in percentage terms. So the percentage gives us area of steel as 5.21 inches square. Now we have to cut, which also gives us dividing the 5.212 inch square with the area of steel of 1 bar, that is number 6, gives us 12 number 6 bars, which is similar to the exterior columns. Number 6 here as well. So the percentage of steel has reduced in above stories here, as these are interior columns, leaves us with 1.47 percentage. Multiplying the percentage with the gross area and dividing with 100 gives us area in inches square. Using number 5 bars gives us 7 number 5 bars, but we don't intend to use the bars lower than 12 as we have to keep the uniform number of bars on each face. So let's take 12 number 5 bars conservatively. First floor column C2, that is exterior columns. Since all bars are uniform, so we delete this typical dimension or the leader line for the individual bar. Dimensioning the column. Now we are required to check for the shear reinforcement or the ties. Starting with exterior columns. First of all, we need to turn off the visibility of interior columns. Display design info and shear reinforcement. Select the highest number from the exterior columns. That is, we are getting 0.12. First of all, we need to know the limitations for intermediate moment reducing frame for ACI code. The spacing S of the ties at columns L shall not be greater than the 4 cases at a length L0. 8 times diameter of the smallest longitudinal bar, 24 times diameter of the tie, half of the smallest column's cross-sectional dimension, or 12 inches. The distance L0 near the support shall not be less than column span divided by 6, maximum column dimension, and 18 inches. The spacing of the ties shall not be greater than twice of spacing at the supports. So right now we will be calculating the parameters for our case. If spacing of the adjacent longitudinal bars is greater than 6, then we will provide alternate ties as shown. But usually we will be providing a uniform spacing of the ties throughout the columns, as the columns are very short and no need to calculate the extent of L0. 8 times diameter of the smallest longitudinal bar gives us 6 inch, 24 diameter times of the half inch bar gives us 12, and the smallest dimension divided by 2 gives us 6 inches. Hence the ties spacing shall not be less than 6 inches. Now calculating the ties spacing coming out from the design. Number of legs into area of each tie bar divided by area of steel, inch square per foot from Etabs. So the spacing of ties comes out to be 3.2 inches for number 4 bars. We will round down the 3.2 inch to 3 inches. Number 4 at 3 inches center to center rings or ties. Since the interior and exterior were getting a similar number of inch square per foot for ties, we will be using the same. Now for the exterior or interior columns. So we are getting a same number here as maximum, that is number 4 at 3 inch center to center. We will be copying this. So now we are done with complete design and detailing of the column. But one thing is left in the structural drawing of the column, that is the notes for the contractor. All the columns are centered on grid line. The FC prime of the column is 4 KSI. You may specify it as cylindrical or cubic strength. The Fi is 60 KSI. Additionally, if the structure was high rise or other, you have to check limits for drift due to seismic loading, drift due to wind loading if the structure was high rise, and torsional irregularity in order to finalize the column sections. Since it was a low rise structure, therefore wind is not defined or it will not govern in design. But in order to understand these limitations concept, you have to go through basics, which I will be discussing in the next video for design of special moment resisting frame.